Hello. So in the following two recordings, we're going to be going over subsequences and how they can be applied to determine convergence of a given sequence. And also, we're going to cover what's called the Bolzano-Weierstrass theorem. One of the pillar theorems of undergraduate analysis. So what is a subsequence? Well, given some sequence X, we first will consider an increasing sequence of natural numbers n1, n2, through nk, dot, dot, dot. Okay, so this is an increasing sequence of natural numbers. And for each of these natural numbers, we're going to pick out terms from the sequence. Okay, so this is a rather maybe cumbersome definition. So maybe it might help if I give an example of something like, suppose your sequence is maybe 1 over 1, 1 over 2, 1 over 3, so forth and so on. Okay, and we want to find a subsequence of the sequence. Well, one possibility would be to say maybe you have 1/2, 1/4, 1/6, so forth and so on. So how would this match up with this definition here? We have some collection of terms from the original sequence. Well, we would say here that, so the indices here are, so here's n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, so forth and so on, right? Well, then we would say that n1 would be equal to 2, n2 would be equal to 4, and then maybe n3 would be equal to 6, and k is going to be equal to 2 times k. So, right, so this is an increasing sequence of natural numbers, and if this is our sequence xn, right, then maybe xn sub 1, comma xn sub 2, comma xn sub 3, so forth and so on. Well, xn sub 1 is x sub 2. So x sub 2 is that. Xn of 2, xn sub 2 is like x of 4, so 1/4. And then the pattern continues. Okay, so this would indeed be a subsequence of x because we have an increasing list of natural numbers. Okay, and then with that increasing list, we pick out those indices from x, and then we put them into a sequence which forms a subsequence. Okay, so that's it's a valid subsequence. Something that would not be a subsequence would be like, say, so why would that not be a subsequence? Well, the indices corresponding to this entry and this entry, they're not increasing, right? So if this was like your n sub 1, and that was your n sub 2, that entry from the sequence at index 2, that index from the sequence has index 1. So the index corresponding to this entry and that entry, that index is bigger than the index associated with that entry. So this would be bad. Okay. So it's It's all about making sure that your indices of your subsequence are indeed increasing, so that when you look at your sequence in here, like this is a sequence, right? A subsequence. So if you look at that inside of the supersequence, I suppose, then you are indeed getting a subsequence, something that is a sequence contained in this sequence. Whereas if you looked at this one, you would bounce back and forth, and it wouldn't necessarily be a subsequence. Okay. So hopefully that makes a little bit of sense. Okay. Now it turns out, so this sequence here is 1 over n, right? We know that this sequence is convergent and its limit is 0. If we look at this subsequence, we're also going to notice that this sequence is going to be convergent and it's also going to converge to 0. In fact, if you take any subsequence, sticking with this definition, any subsequence of this, maybe you have like 1/3 and then 1/9 and then 1/27. Any subsequence of that is also going to converge to 0. If you just played around with it and tried to come up with a subsequence that didn't converge, you would never find such a sequence. And the reason for that is the following theorem. So this is theorem 3.4.2. Okay, and this theorem states that if X is a sequence of reals that converges to X, then any subsequence of X also converges to little x. Okay, so this is the theorem. So let's go ahead and prove this. In fact, I'm probably going to run out of room right here, so I'm going to prove it over here. Okay, so proof. So maybe start by saying, suppose limit of the sequence xn is equal to x, and let epsilon be greater than 0. Okay, so then by definition, there is some natural number k some index that cuts the sequence off, such that the distance from the sequence to the limit is at most epsilon whenever n is greater than or equal to k, right? That's just the definition of convergence. Okay. Now, suppose we need to consider some subsequence and show that it also converges to that limit. So Next, maybe suppose x in sub k is a subsequence of x. Okay, and x is just the sequence in question, right? Now, one thing that I forgot to note over here in the definition is that because this is a strictly increasing sequence of integers that make up the indices of our subsequence, because it's strictly increasing, the k value here, right? These indices are going to be greater than or equal to the subscript, right? The subscript here. So like n1 is greater than or equal to 1, n2 is greater than or equal to 2, nk is greater than or equal to k. Okay. And it's something that you should technically prove, and you can prove that by using induction, but it is true. Okay. So then we can say maybe like since n sub k is greater than or equal to k, little k, if k is greater than or equal to capital K, okay, then n sub k is also greater than or equal to capital K, right? Because n sub k is greater than or equal to that, if that's true, then that must be true. And so n sub k is just an index, right? It's just an index. So if n sub k is greater than or equal to k, we know that this value here must be within epsilon to x. Must be within distance epsilon to x, because any index that's bigger than k for the supersequence has to satisfy this because it converges. So since this is just an index, if that index is greater than or equal to k, then we know the terms from that sequence have to be within distance epsilon to the limit. Thus, the limit of the subsequence also equals x. Here you go. Okay. Okay, so this is important to note, right? It tells us something about the limiting behaviors of subsequence, but it also tells you about the divergence behavior of sequences. For example, what happens when you negate this theorem? Right, so what does the theorem state? So we break it down into logic. It's so it's like if limit of xn equals x, then the limit of any subsequence also equals x. And this is for all, right? This is for all subsequences of x, right? So if the limit can, maybe I should write if xn converges, and that, then that for all subsequences. So I was kind of abbreviating too much. So if that and that, then that for all subsequences. So if you look at this in negation, not negation, I'm sorry, contrapositive. right? Because the contrapositive of a conditional has the same truth value as the conditional, the original conditional. So not this implies not that. So, for example, a consequence of this is that if you have two subsequences that converge to two separate limits, then this is not going to converge. The original sequence is not going to converge. So in this chapter, in section 3.4, there's a collection of what are called divergence criteria that I suggest that you look at. But really, all they are negations of the original definition of convergence. If you negate that, you get a divergence criteria. If you negate, or not negate, if you look at the contrapositive and negations of these statements, you get a series of convergent or divergence criteria. Okay, but that's all I'm going to speak of that for now, because I want to get to the main goal of these recordings for this section, and that's this famous Bolzano-Weierstrass theorem. So I'm going to stop this recording here, and then we'll pick back up with the first proof of the Bolzano-Weierstrass theorem.